Again, for day 2 of our workshop on system architecture for Society 5.0. I will share my screen in just a few seconds, but I was wondering if somebody would be willing to share a little bit about the work that you did yesterday afternoon. And I'm speaking specifically about exercise 1, which was a system problem statement, and exercise 2, which was the stakeholder value network. So my question is, would anybody in the group be willing to just share a couple of thoughts about the exercises that you did? Maybe we also have some participants or some TAs. So exercise 1 was a system problem statement for mobility, and exercise 2, stakeholder value network for mobility. Would anybody be willing to share some ideas or some thoughts from yesterday before we start? Don't be shy. Let me see if you want to, you can raise your hand, I believe. Do we have any volunteers? Masahiro from Team 9, would you be willing to say a few words by turning on your microphone? Nihongo is okay.
Morning. This is Hiro speaking. SPS, that kind of fixed form is really useful to share at the very first stage of the project within a member of the project, I thought.
Thank you very much, Hiro. That was very helpful. Thank you. And then we have from Team 14, Takashi. Dozo.
Good morning, Odi. I just...
Oh, Mr. Kono-san. I didn't realize you were on a team, actually. Good morning, Kono-san. How are you?
Thank you. Yeah, I'm
that was funny.
Team member of the group 14.
I just realized that.
Okay, thank you. Yeah, it is very useful to use the SPS, but I just mentioned on the chat room that I want TA to share us about the place of the Google Doc of the yesterday's working place, because maybe every student disappeared about the information of the URL of the Google Docs. So yeah, that's the information I just put on the chat.
Wonderful, wonderful. Thank you very much. Do we have any comments about the stakeholder value network? Yeah, I see Ono-san just posted the link. That's very good. Any comments on the stakeholder work that you did?
Ali, this is Brian. I was not on a team also, but I did take a look at this morning, the various stakeholder value networks, and I was impressed. I was impressed by the diversity. So we're going to try to assemble these in a way, because I think the results were quite impressive.
Mm-hmm. We have a nice comment from Takahara-san from Team 1. Would you like to share?
Thanks. I'm Shusuke, and I think the one thing that we can find very useful by using that I forgot the name of it, but I'm sorry. Using technique was being able to, thoroughly analyze what is going on in the domain that we have chosen, so that we can list it out almost all stakeholders and try to figure out the relationship between them. Because it is necessary for us to figure out the relationship. We can kind of like figure out what is actually going on that we may have missed even if we didn't use this technique to analyze the situation.
Mm-hmm. And Shusuke, you mentioned in particular the hidden relationships. So the relationships that if you are the focal stakeholder, they don't involve you. They're a relationship between two other stakeholders, and therefore they are hidden from you or indirect. You mentioned that specifically, is that right?
Yes, it is. If I think only about hub and spoke model, I don't think I could find out the loop that is probably the most important insight that we can get from using S.
Okay, very good.
SB something.
Thank you very much. SVN, yeah, SVN, Stakeholder Value Network. And then we have Okutsu-san, Team 11.
So I think this process is helpful to communicate and share the same understanding with system architect and stakeholders.
Mm-hmm, mm-hmm. Very good, very good. Thank you for your comments. Okay, very good. So thanks for your comments and contributions. So let's start with the new lecture. I want to make sure that you can see the slides. Can somebody confirm? Can you see them?
I can.
Thank you. Arigato. Okay, good. So let's start now with the first lecture this morning. And there are three topics I would like to cover. First, just discuss some case examples of complex systems. We alluded to these yesterday, but I want to come back to these examples in transportation, in communications, and also in energy. The second part of the lecture, we will discuss the life cycle properties, also known as ilities, and what is the relationship between these life cycle properties. And then I will finish the discussion before we have a break on the topic of complexity. What is complexity? How to quantify complexity, and why is it important to actively manage the complexity of a system? So let's start with the case examples. And just up front, the key message that I would like to give you this morning is that if we think about the discussion yesterday and the material we presented to you, I think it would be easy to get the impression that systems design, system architecture is kind of an easy topic, that it's simple. And the reason is because as engineers, as policymakers, as scientists, maybe as lawyers, as government workers, we would like to build ideal systems, meaning systems that deliver great value to society and they don't have any problems or any downsides. However, we know that real systems do not behave exactly as we want them to. And you remember I introduced yesterday the notion of emergence, and emergence is essential in order to deliver value, but emergence can also have a dark side. And therefore, systems are not really behaving in an ideal manner, usually. And this is why we need to understand how systems behave over their whole life cycle, not just at the very beginning. And that's the topic of life cycle properties, or ilities. And then the last topic or key message here is that as complexity increases in systems, we need to actively manage it. So I'm going to come back now to the three spines that we introduced yesterday. And you remember going back in time to the Industrial Revolution, the time of the great inventions, and then the scaling up of the highways, the telephone network, the electrical power grid, which has led us to the complex multimodal transportation system, the communication system, and the energy system, which are now increasingly being connected to each other and are interacting with each other in a number of ways. And so that is what I'd like to discuss with you. A very interesting exercise was done in the United States roughly 10, 12 years ago at the turn of the 21st century. There were two committees that were put in place by the National Academy of Engineering. The first committee published its report in 2003, and their job was, in a sense, easy and difficult, is to look back at the 20th century and essentially select the top 20 greatest accomplishments of engineering or technology in the 20th century. And this is the list that they came up with. I do not think this list is in any particular order. And as you look through the list, it's quite a mix of things. Some of these things are products or systems, like the automobile, for example. Air conditioning and refrigeration. Those of you that live in very warm climate, maybe some of you are from Okinawa. I've never been in Okinawa. I would love to go, but I hear it's quite warm and the climate is very different than in Tokyo. So air conditioning was a game changer, life changer as a technology. And then on the right side, you see the results of another committee that was put in place 5 years later, also by the National Academy of Engineering. And their task was to project in the future what are the grand challenges, for engineering, but for society in general. And so they came up with a different list of 14 grand challenges. Now, why one committee came up with a list of 20 and the other committee with a list of 14, I can't answer that question. But what is interesting is that when you compare the two lists against each other, and so I'm just going to do this for a couple of the examples. So if you think about electrification the electrification that happened mainly in the 20th century, even though it started in the late 19th century, most of the energy for electrical power generation came from coal. Now, that worked fine for a while, but coal, especially in the early years, coal was a quite dirty technology. And that's why, a lot of cities, industrial cities in particular, where black and soot was deposited everywhere on the buildings, in people's lungs. And so, of course, we want to continue electrification, but reducing the carbon emissions. So two of the grand challenges, making solar energy economical, and number three, developing carbon sequestration methods, essentially taking the carbon back out of the atmosphere. These two challenges, if you think about it, are a direct result of number one, electrification. Another example, which of course is very, very close to the mission of the IPA and the DADC, is the internet, which is number 13, one of the big accomplishments of the 20th century. But if we think about the architecture of the internet, and particularly the protocols, and here I'm referring particularly to the TCP/IP protocol. The original TCP/IP protocol had doesn't really have any specific protections in terms of cybersecurity. In other words, it's quite easy in the original TCP/IP protocol to pretend that you are somebody that you're not actually. So to impersonate a server or to pretend that you are somewhere on the internet, but you're in fact somewhere completely different. And so securing cyberspace is one of the major challenges of our century. And it links to this to number 13. And then the final one I want to mention here is nuclear technologies, since we're going to talk a bit more about them. And of course, we know that one of the byproducts of nuclear fission, so splitting uranium, is plutonium, which is one of the feedstocks for nuclear weapons. And so this is a big issue. And so the downsides of nuclear technologies, managing the potential downsides of nuclear technologies, is a major challenge in our century. Thinking about it in a simpler way, and I've heard it said by our former Dean of Engineering, he said it very well. He said, the 21st century is about repairing the successes of the 20th century. I think it's a very poignant way to say that all these great systems you see on the left side have downsides and complexities and emergence that we maybe didn't expect, and that we now need to think about them in a much more deliberate way. So coming back to our engineering systems classification, I just want to talk now about 3 of those systems, the air transport system, satellite constellations, as well as nuclear energy. So the first one of these is the air transportation system. And the air transportation system has, I think, a very interesting history. It started in the 1920s or 1930s, depending on how you count. And in the United States in particular, one aircraft, the DC-3, had a big impact. It was the first aircraft that was so efficient that you could carry passengers and actually make a profit. Before then, all of air transportation had to be subsidized by the government, mainly for carrying mail. Okay, so after the DC-3, the air transportation system started growing, especially after World War II. And what you see on this picture is a representation of the air transportation system just in the continental United States. And what's interesting about this representation is that it decomposes the air transport system into 4 layers. And so the top layer is the distribution of the population. And it's what causes the latent demand for air travel, cargo and people. We're going to focus in the next layer on the passenger flows. And these are primarily flows between, major or mid-sized metropolitan areas. The next layer is the discrete satisfaction of this demand, these passenger flows, with actual flights. And then finally, the 4th layer is the infrastructure that is needed to support the system, to enable the system, which includes both airports, but it also includes air traffic control centers and navigational aids. And so by decomposing the system into these layers, on the right side, we can now analyze the system in terms of system performance, but also many other issues. For example, if you look at the transportation demand and the passenger traffic layers, well, that's the world of intermodal transportation. Air transportation is not the only way to travel, and there's a direct competition of air transportation with highways and rail. Of course, in Japan, you are all very aware of this. And, if you travel from Tokyo to Osaka, or Tokyo to Fukuoka, or Hokkaido, you have many choices. And the rail system in Japan is really very, very impressive. And so air transportation is not competitive on some routes, but it is competitive on other routes. Then we have competition between airlines. The airline industry has typically been very sensitive to boom and bust cycles, very sensitive to the price of jet fuel. And so there are many bankruptcies in the airline industry and consolidation. We are also increasingly worried about emissions from air transportation and capacity inadequacy. This is not an issue right now during COVID. In fact, air traffic is down about 60 to 70% for the year in 2020. And we expect that it will recover in 2021, but it will take several years to recover. And then finally, of course, we are worried about safety. Air transportation is much safer than it has ever been. Nevertheless, we still have accidents. And so we need to understand the root of these accidents and make sure it's as safe a system as it can be. So if we go back to our system representation, the form of the system is it's an air transportation network. The overall function is to transport people and cargo over large distances, and each of the entities in the system, the aircraft, the airports, the air traffic control centers, have specific entity-level functions like flying, departing and arriving, and controlling, of course, the flow in the system. And so the value comes from the system function, but we do have emergence of undesired behaviors that I mentioned on the previous chart. And so these include the bankruptcies of airlines, delays or congestion, pollution, and accidents. Each of those is going to be related to one of the life cycle properties that we need to think about when we design or improve a system. So profitability relates to the bankruptcies. Delays relates to the scalability of the system. How many passengers, how much traffic can the system actually support? Pollution relates to sustainability, and of course, accidents relate to safety. And as we are designing or improving or investing in these systems, we often have to make trade-offs. For example, it might be possible to improve the safety of the system by increasing the distance between aircraft, having fewer aircraft depart and land, which increases safety, but maybe reduces scalability and profitability. So one of the key challenges in Society 5.0 is, first of all, identifying these life cycle properties and understanding the priority among them. The next example I want to mention here is satellite constellations. You know, when I was a younger man in the 1990s and working on my PhD, coming back from industry to MIT, satellite constellations were a very exciting topic. For example, in the United States, there were two of them, Globalstar and Iridium, that were being launched with great expectations. Unfortunately, both of these satellite constellations, even though they were technically successful, were financially unsuccessful, and both of these went bankrupt. And for about, I would say, 10 to 15 years, there was a real lack of interest or skepticism regarding satellite constellations. This has changed, and we have a new golden age of satellite constellations. The one that I'm showing you here is currently in deployment. It's called Starlink, and it is being built by SpaceX, the company SpaceX. And up to now, they have launched 955 satellites into orbit, and they're expecting to be fully operational probably next year. There's a beta testing service now underway. Of course, we have great expectations again for Starlink, and the function of the system is to provide connectivity to allow you to connect to the internet at quite high speeds, about 20 megabits per second, anywhere in the world. And this is done with user terminals, satellites, and ground stations that receive and transmit signals, and the flow is controlled in the constellation by ground stations. And so here you would think, well, what could be possible negative emergence or undesired behaviors? Well, it turns out there are some. And two of them have been discussed and reported quite a bit in the scientific literature, you know, in the press as well. And so I'll mention them. The first one is the increase in space debris. And so by launching thousands of satellites into very specific orbits in low Earth orbit, we are increasing the population and the density of objects in Earth orbit. And so it is possible that this will lead to an increased number of collisions and the generation of additional space debris. There is such a thing as the Kessler syndrome, the Kessler syndrome is been predicted as a situation where essentially an entire orbital band goes unstable because more collisions cause more future collisions, cause more debris, and essentially you could, we could get into the situation where an entire orbit becomes full of space debris and is unusable for any spacecraft. And a second phenomenon that has occurred with Starlink is light pollution. So the reflection from the sun of these satellites back onto Earth is quite a problem for astronomers. And this was discovered, the magnitude of this problem was discovered after the first batches of satellites were launched. And in the more recent versions of these satellites, SpaceX has added a shade to reduce this reflection, but it's not a completely solved problem yet. And so I would argue that space debris has to do with sustainability, and light pollution has to do with interoperability. And then the third system, which we briefly mentioned yesterday, I think is nuclear power. Now, I didn't study nuclear engineering. I think we have a well-known nuclear science and engineering department at MIT, and we actually have a reactor on campus, a small nuclear reactor on campus, primarily for research purposes. And so the technology is, I think, well understood. It's quite mature at this point. And some countries, including, I think, historically, Japan, France, the United States, have deployed a large amount of nuclear power, which does have a very low, relatively speaking, relatively low footprint, of course, carbon footprint. So if we look at it as a system, we have the electrical grid, which provides electrical power, and we have nuclear plants. We have other sources of power as well, but I'm focusing here on the nuclear plant, which are generating electricity. We have the high voltage transmission lines that are sending the electricity or transporting the energy, across the country or the region. And then we always have one or more control centers, and the job of the control center is to keep the voltage of the grid within a very, very narrow tolerance, essentially balancing supply and demand. But again, even in this case, we have potential negative emergence or undesired behaviors, such as power outages and reactor meltdowns, or even worse, radiation poisoning, which relates to sustainability, safety, and reliability. And so we did mention this yesterday, the 10-year anniversary of the Fukushima Daiichi nuclear power plant accident is on everybody's mind. And I think thinking about it, the positives, the downsides, and the societal implications of such events is very important for us. Okay, so I'm going to stop here for just a minute and see if there are any questions or comments in the chat. So Brian, I don't know if you could monitor the chat and see if there's any comments about any of the three case studies we just went through quickly.
Yes, sir, I'm monitoring.
By the way, I did look at the chat when we talked about nuclear power yesterday. I think it was a difficult conversation because it is a difficult conversation. But one of you mentioned the research that is happening in fusion power, and so I found that to be very interesting. And I think investment in fusion, which in a sense is safer than fission, is absolutely very important. And I think there are several large projects around the world, like Project ITER, which I think Japan is participating in, yes. that could be very, very promising, but we do have to be patient. It will take time to be net energy positive. So I don't know exactly, I don't remember who mentioned the research into nuclear fusion, but you're welcome to...
And there was I think, Ali, 2 points. One is there was a broad discussion generally about not only fusion, but also next generation capabilities. But we have a new question here from Team 14. Could you illustrate the relation between 20C and 21C again? I could not catch it if it becomes more complicated or simplified. I think C is century, 20C is technology, and 21C technology.
Yes, yes, yes.
So C
I
must be
understand.
century.
Yes, let me go back here for just a second. I think the question refers to this chart. Is that correct? Yeah, 20th century and 21st century.
Yes.
So these two lists were made by two different committees that did not speak to each other. The committee on the left made this list, and by the way, these I think these links are still valid. These reports are still available. On the left, we have a backward-looking list from the beginning of the 21st century, looking back toward the 20th century and saying, what are all the great things that engineers and scientists and society has created to make society better? And they met for several months, and I'm sure they had a lot of debates, and that was the result of their deliberation. And often when you have a large committee, you will get lists like this. And my point here is not to argue whether they're missing some major accomplishments are missing, but it is quite an interesting list from different sectors. The list on the right-hand side was put together by a completely different committee, looking forward, from 2000 to the year 2100. What are the big challenges of society from their point of view? But what wasn't done explicitly, and what I'm trying to do here, is to get you to think about the connection between these two lists. And the point is that, yes, a lot of all the things on the left side are really amazing technical accomplishments, and in many ways have changed people's lives, have made society better in many ways, have increased our quality of life collectively. However, there are some downsides. There are some, especially if these systems got larger and scaled up and started to connect with each other, there were some big challenges at the level of a country, at the level of our whole planet, that we have to address. And that's the list on the right-hand side. So my encouragement to you is the links that I'm showing you here, these red arrows, I think it's just a very small sample out of possible connections that can be made. And so when you think about Society 5.0, the mission of DADC, but more broadly, Society 5.0, it is this list on the right-hand side that could serve as a good starting point. And many of these challenges, of course, have to do with information technologies. Not all of them, but many of them do. Okay, Brian, is that helpful?
Yes.
Okay. Was there another question?
Yes, from Takahara-san. Can I think of external diseconomies as a part of negative emergence? I feel capitalism's external diseconomies are under hard scrutiny these days, as seen in phrases like stakeholder capitalism or SDGs. Mm-hmm. Is emergence the way to describe the same thing, but from an engineering perspective?
I think that's right. Yeah, I would agree with that. I think emergence is let's say, engineering or system architectural explanation for why these negative aspects can occur. Economists discuss this as externalities. Essentially, they are negative value created by systems that nobody is really paying for, at least not in the immediate term. In the long term, of course, we're all paying for some of these downsides, like, accidents, like pollution, like cyber attacks. All of those things cause damages or negative value, which eventually society has to pay for and absorb. And so rather than dealing with them in a passive way, what we want to do in the future in Society 5.0 as system architects is to build properties into our systems that maybe not eliminate completely, but minimize some of these externalities. Okay? So this is actually a very good transition to the next topic on lifecycle properties or ilities. And I think a lot of people always wonder, especially if English is not your mother tongue, this word ilities, which you will probably not find in the dictionary. Where does it come from? Well, it comes from the fact that almost all of the words that we're going to talk about next end in ility. So maintainability, reliability, scalability, sustainability. And not all of them, but almost all of them do. And so collectively, we refer to them as the ilities. So to understand the ilities, and I have to tell you, I personally have a very strong passion for these ilities, to understand them, to make them more, that we can design and measure them more explicitly. That's been part of my mission as an academic over the last 20 years. And maybe it started with my experience as a young man growing up in Switzerland. I did my military service in Switzerland quite young. I was 18 when I did my boot camp. And I wanted to be a pilot. That was my dream, to be a fighter pilot. Unfortunately, as you can see, I'm wearing glasses, and I was wearing glasses already at that age. So I got eliminated from the pool of potential fighter pilot candidates because my eyesight was insufficient. So the next best thing that I was offered was to be an airplane mechanic, repairing airplanes, fueling them, turning them around between flights. And so I accepted that. And in hindsight, it turned out to be a blessing because it was very, very interesting. I got to learn about airplanes and the subsystems, how to operate. And I got to see firsthand when a system is designed to be maintained, easily understood, easily repaired, and when it is not. And so I think my interest in these life cycle topics started already very early on. And so what does it mean, life cycle management? It means the things you have to do, not just during design or manufacturing, but during the whole life cycle of the system. And that includes a long list of things as shown here. So daily operations and monitoring, training, certification, dealing with small and large failures or anomalies, protecting the system from random or targeted attacks. And then, of course, sharing and archiving and using the data produced by these systems. And that's, I think, where we see the biggest change in the last 5 or 10 years is the amount of data generated by all these systems. And actually our ability to use that data increasingly to improve operations has really, really changed. So machine learning, artificial intelligence, all of that would be impossible if we didn't have the data from these systems. So a cartoon view of what a system lifecycle is shown here. I'm not going to talk about it too much, but this is the first part of the life cycle where we conceive, design, and then implement the system. And you can see at the bottom here, these little stick figures represent some of the key stakeholders, the customers, the users, the architects, designers, system engineers, inside the boundary of the system. And then, of course, outside the boundary, we have our environment, which is the technological, economic, political, social, and also the natural environment. And And I think many of us, particularly us who grew up or have a technical education, we spend 80–90% of our thoughts and efforts on the early part of the life cycle. And indeed, for new systems, the early part of the life cycle is very important. But the second part of the life cycle is extremely important in terms of delivering the actual value from the system and deciding whether the system will be successful or unsuccessful, short-lived or long-lived. And so operations, monitoring the usage of the system. And you can see here, I'm showing, with this triangle cartoon, that's the physical system that we're interested in. And then with dashed lines here, I'm showing a virtual version of the system. So one of the, I think, really interesting topics and emerging, say, industries and capabilities is the notion of a digital twin. A digital twin is a virtual version of your real physical system that is a very accurate representation. So you can simulate, you can understand failures, you can maybe predict the behavior of the system before certain events happen. They've already happened in the digital twin, and this could be extremely valuable. And then eventually, we upgrade the system, and eventually the system degrades and is liquidated. My observation, particularly when it comes to infrastructure systems, is that these systems often are used much, much longer than they were originally designed to be used. So one example, I think we might have alluded to before, but you may be familiar with, is the space shuttle. The space shuttle that was first designed in 1971 and retired in 2011. And I think it's a very interesting example of thinking about the whole life cycle after the life cycle has been has concluded. You see here in this chart the expenditures that were the money that was spent on the space shuttle program, and we know exactly how much was spent because it was a taxpayer-funded program, not a private program. And so we know that in total, the United States spent $192 billion on the space shuttle over the course of about 40 years. And with that $192 billion, we carried out 135 missions. 2 of those were lost. This was the Challenger and the Columbia accidents. But great accomplishments were, of course, achieved as well, including the deployment of the Hubble Space Telescope, which has given us unprecedented views of the cosmos, and of course the construction of the International Space Station, where Japan, with your Kibo module, has made a major contribution. Nevertheless, if you take the ratio of 192 billion divided by 135, you arrive at a figure which is astounding. About $1.5 billion per flight or per mission. And that was not exactly what had been promised in 1970, early 1970s to the US Congress. What was promised was this. So this picture here is actually from one of the briefings that was given in the early 1970s to Congress. This is what we wanted. Almost like airline operations, you can see the orbiter in a hangar. You see how shiny the floor is, nice and polished. There's only a few people standing around. A satellite is being lowered into the bay, the payload bay. And the prediction was that there would be about 1 flight per week, okay, about 50 flights per year. This is what we actually got, okay? So this is an actual picture from the orbiter processing facility, which I visited several times. And I assure you, the orbiter is inside there. You just can't see it because there's the scaffolding and there's so much equipment. And the reason is that between flights, so much work was required on the vehicle to get it to fly again safely. Particularly the thermal protection system and the engines required a lot of refurbishment. And so why did that happen? The difference between what was promised and what was delivered. I would argue that one of the main issues was that not enough thinking and money was spent on the property of maintainability, being able to maintain, easily access equipment, easily replace equipment between flights to reduce the operating cost. So in essence, what the US Congress did was to reduce development costs and cap it. But by doing that, they ballooned the operating cost of the system. And of course, there were some warnings about this by some smart people. But in the end, not enough was spent up front. And I think it at least partially contributed to the loss of 2 missions. And it certainly contributed to the ballooning and almost explosion of the operating costs beyond what had been promised. So the key point for you to remember here is when you have the chance to design and architect a new system, make sure you really think carefully about those long-term life cycle properties and which ones are the most important to you. And in order to get the properties you want, you need to invest in them. You need to architect them into the system, because after you've made your key decisions, it's very difficult to recover. All right, so let me talk a little bit more in general what the ilities are. So like I mentioned, complex engineering systems have long lifetimes, decades, or even centuries sometimes. They are properties of systems that often manifest themselves only after the system has been put into initial use. They are not the primary functional requirements of the system's performance, but concern wider impacts with respect to time and the set of stakeholders that are involved with the system. And there is a lot of research, as I will show you, on the ilities, but usually only one at a time. Not a lot of research on how do these life cycle properties or ilities connect to each other. So the question we answered here was, well, what are the most prevalent or most important life cycle properties? What is the relationship between them? And how can we use this information for better system design or better system architecture? So I'll talk to you about 2 methods to answer these questions. The first one is called a prevalence analysis. And the second one were some human cognitive experiments that we did. So on the first one, the prevalence analysis, this is pretty straightforward. So what this involved was to search for either journal articles in the scientific literature or just mentions on the internet of a particular keyword involving one of these life cycle properties. And the result is what you see here. So in descending order, by far, the most important life cycle property is quality. And I think, I feel like I'm preaching to the choir, because quality, I think, is something that Japan is extremely famous for and very well known for. The problem with quality is that it has a lot of different connotations. And so it's quite a broad concept. Reliability, then we have safety, flexibility, robustness, and so forth. What's interesting, if you look at the 2 bars, so the black bar is the scientific articles in thousands of articles, and the gray bars are the hits on Google in millions of hits. Some of these life cycle properties are what the common usage is leading, meaning that a lot of people talk about them. There's a lot of policymakers involved with them. The general public is very aware, and sustainability is a good example. But the scientific literature, our ability to really understand, measure, and architect to get this property is not as developed. And then there's some other examples where it's the opposite situation, where there's a lot of scientific literature and a lot of theory, but not a lot of people in the public really care about it. So the example here is modularity. There's a lot of interest in modularity in the system architecture community, making systems modular. But the interest in modularity in the general public is not terribly large. So in this case, I would say academic or scientific interest is leading. Another way to look at these life cycle properties is to look at them over time cumulatively. And in this graph, we're looking at the cumulative number of journal articles published where a particular ILITI, life cycle property, is in the title or in the abstract of the article, going all the way back to 1884, which is the beginning of this particular database. So what's interesting, and you can see it's logarithmic. It's a logarithmic chart. So it's really fascinating. There are articles from the late 19th century, like 1880s, that talk about safety already, safety as a property of a system. And one example of such a paper is a paper that talks about lighting in mines. Of course, mines can be very dangerous, and they have been dangerous in the past. But this particular article looked at the difference in accidents and fatalities in mines, in different mines, as a function of how much lighting was provided in those mines. Isn't that amazing? This is a scientific paper from the 1880s. And so safety for sure has been on our minds for a long time. Then we have some life cycle properties that became, I think, important in the middle of the 20th century. So, before and after World War II, for example, usability, maintainability. So not just using and maintaining military equipment, but after the war, of course, the idea of designing for maintainability, designing for usability was diffused into the commercial markets. And then the third group of life cycle properties are much more recent, since the 1970s or 80s. So these are properties where we're really thinking big. Evolvability, the ability of a system to evolve and change, as its purpose, as its set of stakeholders changes, almost like a biological ecosystem. Recyclability, sustainability, interoperability. These are much more recent, and you can see the slope here is much steeper, meaning that the research we do, the knowledge we gain about these life cycle properties is increasing quite fast. The other thing we can do is, and you will actually use this graph here in exercise 3 this afternoon, is to think about how are these life cycle properties linked to each other? Are they like siblings? Are they like cousins? Or is there no direct relationship between them at all? So the graph that you see here was constructed by looking at the ratio of articles that mention 2 of these life cycle properties together. So if that ratio is 1, it means, for example, whenever we talk about quality, we also talk about safety. So quality and safety seem to have a very strong link because we have a thick line here. The thickness of the line is the strength of the relationship between these 2 concepts. And so if we look at this, we can see the original ILITIs, the ones we've known for over 100 years: quality, safety, flexibility, reliability. They're in the center of this graph. The life cycle properties that are more recent, such as interoperability, evolvability, agility, they tend to be on the periphery of this graph, but they are linked. The other thing that's interesting is, I'm going to use some highlighting here, is we can think of these falling into 3 main clusters. So quality, durability, repairability, maintainability, all of those are really related to the question of, is the system implemented well? Is it made well with high quality from the very beginning, even early in life? The next group of these here on the right side, flexibility, extensibility, adaptability, scalability, they're slightly different. They have different definitions and different meaning, but they are related to each other. Essentially, the question here is it easy to modify the system? Is it easy to change the system's configuration over time? And then finally, the third set of abilities on the lower part of the graph, quality, sustainability, resilience, robustness, safety, those are related to does the system perform well over time under uncertainty? So under, let's say, shocks or disturbances, either inside the system or coming from the outside of the system. And so I think we gain quite a bit of insight from this type of analysis. Now, let me talk to you briefly about the second approach that we took, which was to ask people, how do you think these lifecycle properties are related to each other? And so here a set of surveys was done with several researchers. 12 experienced system designers and researchers were presented this list of 15 lifecycle properties. And you can see a definition for each of them. So for example, agility is the ability of a system to change in a timely fashion, so quickly. Interoperability is the ability of a system to effectively interact with other systems, and so forth. So the question was, what is the relationship, and do these lifecycle properties form either a network or a hierarchy? And this was done in 2 rounds. So in the first round, the groups were separated, and each group had to construct their own graph, and we call it a means ends. So what are the means and what is the end between these lifecycle properties? So you can see that each group came up with, their own version of a graph of lifecycle properties. Then what was done in the second round was to combine the results from these 4 groups to create a single integrated means to end hierarchy of lifecycle properties. And the lines that you see here have a meaning. So a solid line means that 3 or 4 out of 4 groups had determined this particular relationship. And if it's a dashed line, it means that 2 out of 4 had found a relationship. And if it was only 1 out of 4 groups, we discarded it. And so if you think about this graph, what comes out of it is quite interesting. We have at the top level something called a lifecycle property called value robustness. And so linking to Brian's lecture yesterday on stakeholder networks, a system that has high value robustness, it continues to deliver value despite a lot of changes in the environment, failures, change in government, change in policy. The system just continues to, maybe not perfectly, but it continues to survive, it continues to operate, and maybe adapt itself. And so below that, you will find survivability, robustness, and changeability. And then if we go to the very lowest level, we find things like, interoperability, so the ability of systems to be connected, reconfigurability, and also modularity. And now we understand that from a general public standpoint, the public doesn't really care about modularity or interoperability or reconfigurability. We as technical people or scientific people, we care about those, but they're just an enabler of the higher level purpose of these systems, which is at the top, which is the value robustness.
Ollie, if I could just mention one question in the chat. They see safety, but there is no security shown in the chart. So would you consider security an ability?
Yeah, I think it's a very good point. Oftentimes, these two concepts are not, say, distinguished enough. I would add security in here. It wasn't part of the. If we go back to the list here, you can see that it wasn't part of the set of 15. The difference is that safety, safety is about preventing loss, preventing accidents. But classical safety is preventing loss due to unintentional failures of the system. So random failures of the system, essentially. And security is preventing loss due to non-random failures of the system, essentially meaning a targeted attack on the system. But absolutely, security should also be included here. It's a very good point. Okay, so let me summarize on lifecycle properties. These are absolutely critical for the long-term value of the system, and for Society 5.0, I think it's worthwhile spending a lot of time on these, really thinking about them deeply. And there are quite a few of them. I would say there's not 100 of them, but there's more than 10. Somewhere between 10 and 20 of these life cycle properties are really the most important. They do form semantic sets, meaning that they are related to each other. Systems that the value of the system is heavily driven by the ability of the system to be robust, which means it continues to operate despite internal or exogenous disturbances, flexible or changeable, and then resilient and survivable over time. And you can think of these ilities or life cycle properties as forming a hierarchy of 2 or 3 levels, as is shown here, where at the top we have robust value delivery, and at the bottom we have the technical and maybe social or even legal enablers of that value delivery. So things like modularity and interoperability are at the lower level, but they're very important enablers of what we want at the top level. And so the question you should ask yourself as a system architect is, what are the most important lifecycle properties you want in your system? And how can you achieve these through good architecture, good design, and good regulations, laws and regulations? Okay, so I'm gonna just pause here for a second. I know this was a bit of a challenging discussion, and see if there's any additional questions or comments.
Yes, from Kono-san, regarding the relations of ilities, what is the meaning of a strong relation, such as a bold arrow? I think co-occurrence means 2 types. Showing similar properties so that it co-occurs, for example, flexible and modulable, or showing opposite property under the context that the system should maintain some balance, for example, open but secure. So what can you say about the relationships amongst these ilities?
Yeah, I think that's extremely insightful. So I agree with those 2 viewpoints. So the first one means that we have one is a prerequisite or perhaps an enabler to the other, and so you can see, for example, modularity has a strong, solid arrow to scalability. Well, that makes sense, because if your system is monolithic, it's not easy to scale it up. But if your system, the architecture of the system decomposes the system into modular units, well, it's quite easy to add additional modules if you thought about this ahead of time. And so modularity and scalability have this one enables the other kind of relationship. And absolutely, openness versus security, I'm not sure I can find a particular example on this chart, but they're like negatively correlated. So we can think of one as the positive correlation, and the other is the negative correlation. And in fact, I don't want to give away too much, but in the exercises this afternoon, both the analysis of the IoT system, but also the e-commerce exercise, that will be exactly the question that we want you to grapple with, is how do you trade off openness, interoperability, openness, ease of access versus security?
Great, thank you. One more question from Satake-san, which is early on or at the beginning of projects, how should one select the ilities, or at least judge the significance of ilities, so that we still have enough budget and time? Are there any tips or frames to be better with this? Every requirement costs money.
That's correct. That's correct. So my recommendation here is to start with your customers or users or stakeholders and build what are called CONOPS, concept of operations. This is a kind of illustration of who will use the system, why will they use it, and how will they use it. And so the two by using SPS discussion yesterday is closely related to that. And you may have more than one customer. You may have different stakeholders using the same system, but for different reasons and different ways. So for each of these, you should construct a concept of operations, or CONOPS. And so that'll give you a list of these CONOPS. And then you should also think about what could go wrong, or what could prevent this concept from operations from being successful. This could be an attack, a failure inside the system, maybe a change in what this particular customer wants in terms of requirements. And so don't just think about the nominal CONOPS, but also the off-nominal CONOPS. And then what you need to do is you need to weigh them. So, one kind of customer or user might be 3 times as important to your system as another type of user. So by weighting then these CONOPS, including the off-nominal operations, you can combine them and come up with somewhat of a ranking of these lifecycle properties. That is not necessarily a perfect process, or just plugging into an equation, but at least it's a start. And certainly you have to iterate with your stakeholders on this. And be clear with them to say, for example, well, if you want the system to be more open and easier to use, less delay, we will probably increase the probability of cyber attacks by maybe 25%. Is that acceptable to you? And oftentimes those discussions don't happen when new systems are being created. And they should happen.
Thank you.
Yeah.
And we'll talk more about this in the remainder of the lecture today.
Okay. So then the last piece I want to discuss with you is about complexity. That's also, I think, one of my favorite topics. I should say that some people have a negative view of complexity to begin with, that complexity is a priori something negative or to be avoided. I think the reality is that complexity can be good. Complexity can be necessary to deliver the level of performance, the lifecycle properties that we are seeking. So in some sense, complexity is unavoidable. The question is, how do we quantify complexity? How much complexity can we reasonably handle? And how do we manage it? And so, one thing that I always tell organizations that I interact with, or the students that we teach at MIT, is if you can't measure it, then you can't manage it. And so that's really my message to you here. And so what am I talking about in terms of complexity? I want to focus for complexity here for a second on the structural or form complexity, Because that, in a sense, when we talk about measurement of complexity, that is the easiest starting point. What are the elements, the entities of the system? How are they linked to each other? And so a simple system is a system that, when you decompose it using the 7 plus or minus 2 rule, so we decompose the system into 7 parts, 7 plus or minus 2 parts. At the level -1 of decomposition, every one of these parts is actually not further decomposable. You have an elementary part. So that could be one line of software instructions. It could be a physical part. So for example, if I look at this pen here, right, it has a cap, it has a felt tip. Inside it has a reservoir. It has a housing. Yeah, it has about 7 parts. So this would qualify as a simple system. Now, the manufacturing plant that creates these pens may not be a simple system, but the pen as a system definitely qualifies. A medium system is one that requires, to get to the basic parts that cannot be taken apart any further, requires 2 or 3 levels of decomposition. So some of the examples that Brian shared with you yesterday that you worked on, Brian, what was it? The coffee maker? Can you remind us? You had a coffee maker?
Toothbrush, laundry machine, coffee maker, and digital camera.
Thank you. So I would put all 4 of those into this category of a medium complexity system. Would you agree?
I certainly would.
Okay.
But their context may not be, as you were saying.
Absolutely. So again, it depends on how we draw the boundary. And then a complex system is one that requires more than 3 levels of decomposition. And, you know, some people ask me sometimes, well, where do you draw the line? How can you justify this? And so an example I give you here is a complex FLIR system. Certainly the all the examples we talked earlier, the satellite constellation, the electric grid, all of those are complex systems. But how do you really know? So I think I have a very simple way of explaining this. I believe that simple systems and medium systems can be fully understood, meaning fully understood, every part, once you've decomposed it to the lowest level, can be fully understood by one single human being. Now, maybe it may take them a lot of time to understand it, but it's understandable by one person, you know, after they have acquired the knowledge. I told you yesterday that I'm from Switzerland originally, and of course, Switzerland is very proud of its watch industry. So if you look at a mechanical watch and you take it apart, and I showed you yesterday in one of the slides a watch mechanism, it has roughly 150 parts. Well, one person can understand every one of those 150 parts and manufacture them and put them together. And it may take, you know, several weeks or months to do that, but it's just at the limit of what one person can do. This, one single individual cannot do. There's too much, too many parts, too much software. There is too much complexity. So what that means is that a system that is structurally or technically complex beyond the reach of a single human being requires, by definition, a team or a larger organization of people to design, to build, to understand. And that's where the world of complex systems begins. So how do we quantify complexity and structural complexity in particular? There's a very large literature on this, but I want to share with you one of the complexity metrics that I find to be both simple and insightful, that we think can explain a lot. And so the fundamental form of this complexity metric is, C1 plus C2 times C3. So this is an addition and this is a multiplication. Now, what do these terms mean? The first term, the C1 term, is the complexity due to the components of the system alone. And this can apply to software as well, not just hardware as shown. So if we take the watch or the car and we disassemble it completely into its constituent parts and lay them out on a table or on a big parking lot, like you see in this picture, well, there still is complexity. Each of those parts, components individually has its own complexity, even if it cannot be taken further apart without breaking it. The second term is due to the pairwise interactions between components. So the relationships or interfaces. As we assemble the system, there will be pairwise interactions between pairs of components. And then the third term, which in a sense is the most interesting one, and is often forgotten when people, many of the simple complexity metrics only count parts, count software lines of code, maybe they count interfaces, but they often neglect the C3 term, which is the key. The C3 term is what we call topological complexity. So when you think of it as a network, is it a simple hub and spoke, like we talked about the stakeholder networks, or is it a complex distributed network? That will have a big impact on the overall complexity of the system. And C3, I think you can hear it in my voice, is the most interesting and potentially impactful of those three factors. So I promise you not too many equations, but here's one of them for those of you that want to go a little bit deeper on this idea. So how do you calculate, each of those three terms? So this is, the first term is the sum of all the component complexities, which we call alpha. So you sum over all the components in the system. This is essentially a matrix. We're summing over the interactions pairwise. Then we have a normalization factor, which is we divide by 1 over n, because remember that we can represent the same system at different levels of abstraction or granularity. And then the third term, this is really the interesting one. This is what we call graph energy. So the interaction matrix is A. In this case, it's just a binary matrix that says this component is connected to this other component. So it looks like a 0-1 matrix. We can calculate the what's called the singular values. We can decompose that A matrix, that adjacency matrix of the system, and calculate a kind of energy of that matrix. And then that's the calculation you see here. Again, the details of that, I'm happy, any of you that are interested to learn more, we have some references on this, but just know that this A matrix that captures the topology of the system, it has a kind of energy that's called graph energy. Now, why is that interesting? Well, it's interesting because, and you've all experienced this in your own lives, that the amount of time or effort it takes to understand or build a system scales with complexity. And so we actually did some experiments here as well with people. And what we asked them to do was a pretty simple task. Some of you might remember from high school in chemistry, if you had chemistry, these kind of molecular models, these stick and ball models. So we gave a number of test subjects the task to rebuild some of these molecules, starting with very simple ones, and then making them more and more and more complex using the structural complexity metric that I showed you. And then on the y-axis, we captured the average time that it took them to build these molecules, including the time to correct any mistakes or errors. And what we found was fascinating. What we found is, you can see it in this curve, is that the average build time was super linear with complexity. So as complexity of what we asked the participants or the test subjects to build increased, their build time increased more than linearly. Not quadratically, but somewhere between linear and quadratic. In fact, if you look at the exponent here, it's about 1.5. And, you know, this explains a lot. It explains a lot about why, you know, building a really complex piece of software is so much harder than building, you know, 3 smaller pieces of software. It explains a lot, this nonlinearity. You can apply this complexity metric to simple systems like cyber-physical systems, like you see here, a component system with 5 components, a valve, a filter, a pump, a motor. And there may be some uncertainties on component complexities. So you might get a distribution of complexity with a mean complexity, you know, and some estimation uncertainty. But the point is that complexity is something that can actually be measured rigorously in a system. And then come back to the C3 term, which was the one that captured the topological complexity. And so here, I think we have a very important point to make about Society 5.0 and the systems that DADC has to deal with. It turns out that the C3 term, once you've normalized it by n, you know, the number of components in the system, has 3 regimes. The centralized architecture looks, you see this picture here, it's like a hub-spoke kind of system. It turns out that for centralized architectures, the C3 term is always smaller than 1, okay? And then the other extreme is a fully distributed, like a mesh network, a distributed architecture. There's no clear hub or central point. The C3 term will always be greater than 2. Most real systems, physical systems, including, you know, the Tokyo metro system, for example, most computer networks, they're in the middle. They're, you know, they're hierarchical. There are some hubs, but they're local hubs or regional hubs. And so for those architectures, the C3 term is somewhere between 1 and 2. All right, so when you're a system architect, when you're designing systems for Society 5.0, this will be one of the key things you have to think about and decide is, what is the degree of centralization or decentralization or distribution that you want to have in your system? And I just want to show you some systems we've studied in my research group. And they're, I would say, you know, medium to high complexity systems in terms of physical products. And what we've observed, on the left, you see an older product, an older architecture, and on the right, a newer one with more capabilities. This example is actually from the Xerox Corporation. I know that Fuji Xerox is very well known, I think, in Japan. So these are printing systems, digital printing machines. And so we decomposed them. We created these graphs for them. And what we found, it was pretty surprising that between the old and the new generation, we have found a 90% increase in overall complexity of the machine. And when you look at the C3 term, I'm just going to look at this most likely number here. We went from 1.36 to 1.8. What does that mean? It means that the system became more distributed, less centralized, and more complex overall. We found the exact same trends for aircraft engines. This is an old generation of an aircraft. This is a Pratt & Whitney 4096 two-spool direct drive engine. And on the right side, you see the very latest generation, which is the gear turbofan engine, which is produced by Pratt & Whitney, which is used among other airplanes, I think on the MRJ, Mitsubishi regional jet uses this kind of architecture. And so here we see a 42% increase in complexity. And again, if we look at the C3 term, it's not quite as extreme as in the printing systems, but we're going from 1.51 to 1.69. meaning that, you know, this system also is becoming more distributed. So this is a trend that we're observing. Okay, so I'm going to come to a close here since I think we're coming up on time. I just want to draw a distinction between complicatedness versus complexity. So the complexity of a system, I hope I've been able to convince you, is something that you can measure, that is objective, quantifiable, similar to, say, the temperature of a system. If you have a reference scale, you should be able to measure the temperature of the system. So we should be able to measure the complexity of the system. Now, the complicatedness is the interpretation of that complexity by human beings or organizations. And as we are developing a system or improving a system, we incur, of course, effort or development cost. And as you saw in the experiments, that development cost is nonlinear. You know, we have this y equals ax b, where the interesting part of it is the exponent b, which we found experimentally to be about 1.5. Now, an organization that has done a lot of similar designs before, they will be able to become more efficient. Another example I can give you is the game Go or chess, for example. Very good Go players, they look at the board differently than novices. They are much more efficient at playing the game. And why is that? It's the case because they play the games using patterns and strategies, not individual moves. So complicatedness is very important, and what drives complicatedness is the complexity of the system, the modularity or design encapsulation, and of course the novelty. How new is the system? How much experience do you have with the system? But there are some other social or cultural factors as well, including, you know, the cognitive capability or bandwidth of your organization. And so what this leads us to, or allows us to do now, is to connect the three dimensions of complexity that we presented to you yesterday, but in a somewhat, let's say, separate way. So we always start with our customers or competitors or stakeholders that levy requirements on the system, and this drives functional complexity. The functional complexity will drive, through engineering, structural complexity or complexity of form, and we can have, of course, a feedback loop here. Brian talked to you about organizational complexity. And so as we have to design a complex system, this can't be done by a single person or even a single team. We need to distribute the development effort across multiple teams, multiple organizations, and that drives organizational complexity. Again, we can have some feedback effects. And then finally, there is also, of course, a link between organizational complexity and functional complexity. Eventually, the outcomes that you care about programmatically, like non-recurring engineering costs and schedule, are coming from the organizational side. So functional complexity, structural complexity, which I focused on a lot in this lecture, and then organizational complexity, which we discussed yesterday, are all linked to each other. And you have to think about all three dimensions. So
Ali, really quick, I know we're running out of time, but Yoshida-san made a wonderful comment in listening that tries to relate complexity to centralization. And he referred to a Japanese phrase, which if I try to translate is kind of the greater the complexity, then the more the decentralization is, and that becomes messy, right? So
Brian, can you say it in Japanese?
Everyone can read it in the chat. How's that?
Wonderful.
So I guess the real question is the amount of centralization or decentralization by itself a characteristic of complexity, or is it a response to complexity, or both?
Both. So so for example, if you think about organizational complexity, that's also something that you can, is it a centralized organization? Is it decentralized? Who has authority? Where are decisions made? That's organizational complexity. Structural complexity, we're referring to the physical system. So if you think about, again, the electrical grid as an example, do you have a few large electricity producing plants, and they push out, I'm saying this in a kind of simpler way, but they're pushing out the electrical power, to the periphery? Or do you have a smart grid with a lot of distributed, renewable energy production mixed with some centralized production, which is where we are today? So no question that the complexity in the electrical grid is increasing.
Well,
so they're linked.
This can lead to, I think we should recommend a whole nother workshop just on complexity. Ohara-san also commented on the relationship between modularity and decentralization. Is decentralization inherently leading to the modularity? Or I would say the question is, does it lead to the benefits of the intended benefits of modularity or not? And I know in my research, what we often look for is not simply the organizational structure and dynamics or the technical structure and dynamics, but the degree that they are aligned, that they're somehow fit. I can have a high performance decentralized organization if we're prepared for that, or I could have a high performance centralized organization depending on the dynamics.
That's true, but one may be more adaptable than the other, for example, right?
Certainly, but those physics are part of the structural part. The organization, the process, and the product system all have nature that changes relatively slowly, and that's what we're trying to understand. What happens when you put them together?
Right. So the role of modularity is most pronounced in this intermediate regime. When C3 is between 1 and 2, that's when the effect of modularity is the greatest. So let me finish by saying that the three systems we talked about, energy, transportation, and communications, are very important, and they're linked to each other. But that's not the end of the story. We really have interconnections with all these other systems: education, finance, water management. And when we think about COVID, I actually have a version of this chart, which I'm not showing you today, that shows COVID. What happened with COVID is that, I think it clearly affects in a great way the healthcare system. However, if you think about it, the effect of COVID and the pandemic, beginning from healthcare, has radiated to many, or most of these other systems now. For example, communications, the amount of internet traffic has I don't know what the exact number is, but I think it's increased a lot this last year, at least 50%. Transportation, many fewer people are using public transport right now. That's a big problem for some organizations like, JR East or JR Central. The educational system is changing in a radical way. And I don't know yet, I don't think any of us know yet, whether we're ever going to go back to the prior, pre-pandemic baseline. The financial system has been impacted. Even water management, you're probably aware that COVID-19, the virus, I should say, can be detected in wastewater. And there are many towns now that are analyzing the wastewater in their town as a leading indicator of infections. So, Kono-san, you asked a question yesterday, a great one, about what are the limits, the boundaries of Society 5.0. And it's not an easy question to answer because of all these interconnections. Nevertheless, I do think it's important to focus on a part of it, because If you say it's everything that's shown here, well, that's a huge scope, and it's difficult to really impact or make change. And so I think I mentioned the engineering systems book. We mentioned Japan in several ways in the book, mainly in a very positive light. We mentioned Shinkansen, which is an amazing system that has very high degree of safety and very high degree of life cycle. We mentioned life cycle properties. We mentioned the Toyota production system, TPS. And keep in mind that this book was published just before the Tohoku earthquake and all of the things that happened since then. So I think we need a new edition. So to leave you with a really big thought, the work that you're doing, the role of Society 5.0 is really critical. And we are somewhat at a tipping point, I think, in our society, where if we do things well, by the year 2100, we could be in a very favorable situation. What does that mean? It means that, we have a stable population, renewable energy, we recycle everything, we have a world in equilibrium, or we could be in a very unfavorable situation, meaning continued population growth, climate change, inequities, even mass starvations and depopulation, and a collapse of our human civilization. And I don't mean to scare you, but I do want to mention an excellent book, which I'm pretty sure exists in a Japanese translation, by Jared Diamond, who's a professor of geography at UCLA, called Collapse. And so he studied how past societies have collapsed and why. And he has 7 major reasons or factors that drove their collapse. The difference with what Diamond describes is that most of those civilizations were isolated from each other, like, for example, on Easter Island. But remember, in this world that we live in, we are all connected. We are all connected. It's difficult to imagine one part of our planet or one society collapsing, but not the other one, because we are so interconnected with each other. So the point is not to scare you, but to encourage you, and to say that socio-technical engineering is very important so that we can improve the odds of a favorable outcome, which is shown on the top of this chart. Okay, so let me summarize. The keys from this message is that complex systems are everywhere. They enable key functions in society. Systems deliver value when they deliver the functions we want, which is transporting people and cargo, delivering electrical power, transmitting information, and many more. However, real systems have emergent properties, and those destroy some of the value through accidents, through pollutions, through failures, and so forth. And so understanding not just the functions of the systems in a narrow sense, but the life cycle properties in a broader sense is key for robust value delivery of these systems over time. So remember the hierarchy of ilities and the need to rank order these ilities as you are architecting and designing the system. What is most important to you? And this afternoon, we will have an explicit exercise where we will ask you for a hypothetical system, but I think a kind of a relevant system, to rank order the top 5 ilities. And we really look forward to seeing what the different teams come up with. And then the final point here is that complexity keeps increasing. More people, globally speaking. I know in Japan the situation is somewhat different in terms of population growth, but nevertheless the expectations for our systems are increasing, and we need to limit or actively manage at least the complexity. And so I think we're going to